So today I'm going to talk about how to bring your neural networks into Upstream MLIR Dialects. And just a brief overview of what I'm going to talk about. So first I will define the problem that I'm going to present and what you will learn. Then the two dialects that we're going to target from the frameworks. And then I will go framework by framework on how to lower that to Upstream dialect. And at the end, you have a small conclusion. So why do I give this talk? When you look at discourse, beginners very often struggle to get their neural network into Upstream MLIR dialects. And I get it, MLIR is not a compiler, but the tensor compiler stuff still is a very big part of Upstream MLIR. And we should not forget that. And the newcomers, they want to play around with MLIR, try tiling, try different passes. But the importers, to get the neural networks into Upstream dialects, they're not part of MLIR. They live in different repositories, in different projects, and that's quite hard for a newcomer to get this fragmentation right. Also, when you look at typical compilers using MLIR, you very often see this image here, where you have like PyTorch, ONNX, JAX, whatever, and then an arrow to your compiler, and it's kind of hidden magic at the end. But from my experience, this part is very complicated and messes up your dependencies very often. So I'm going to talk about how to bring a model to LINAC or TOSA. I'm going to show you which projects you need to use for which framework, where to find the code and examples, and also some tips and tricks on how to use them. I've used almost every single one of those, so I'll also give you like a bit of my own experience. Take it with a grain of salt, might be different for you. Also very important, we have April 2025, and this might change in the future, so keep that in mind when you look for this talk in the distant future. Let me give you a quick example of the two dialects we're going to target. So the first major one is LINAC, and LINAC comes in two flavors. We have something called named ops and generic ops. And named ops are just syntactic sugar for specific generic ops, like a matmul, things like that. I would say it's the main code-gen dialect in MLIR. It's probably right, maybe one of the most used ones. And the input frameworks I'm going to show most often try to lower to the named op variants just to preserve a bit more information. And then below you have a small example of LINAC. On the other hand, you have TOSA, which stands for Tensor Operator Set Architecture. There was a talk yesterday in the workshop about it. It's tied to a spec. And the goal is to have a minimal and stable set of tensor operators. It is the only ML graph dialect upstream, and it's as much an input dialect as an output dialect, because there are also some backends using the TOSA bytecode for their downstream compilers. Let's talk about the first framework, LiteRT. Probably most of you know it as TensorFlow Lite. They renamed it last year, so it's a bit more decoupled from TensorFlow. LiteRT is a very lightweight ML runtime, optimized for mobile and edge devices, and it has a stable flat buffer file format, normally with TF-Lite at the end. It supports quantization and model optimization. It's quite nice if you want to have fully integer networks. And the original design was for CNNs and RNNs, but you can also normally compile transformers with it, even though some things like KV caching, all of that, need to be handled by the surrounding program using the TF-Lite file. And it's widely used in Android, iOS, and embedded Linux devices. So this one is one of the OG frameworks. How does the lowering work here? So you have the TF-Lite flat buffer file, and inside of TensorFlow, you have a deserialization step, which is almost a one-to-one conversion to the TF-Lite dialect. And then also in TensorFlow, there's the lowering from TF-Lite to TOSA. At the moment, I think you need two binaries. I'm not super sure, maybe someone can correct me if I'm wrong, but you need a flat buffer translate binary to translate the flat buffer file to the MLIR dialect, and then you can use tfopt to convert TensorFlow Lite to TOSA. There was a Python API to do that, they removed it now. I think it was because ARM wanted to contribute more, and that was in the way. But maybe some ARM people can comment on that later. And then below, you see actually an example of the IR we get in TOSA. And as I said, it's full integer, I32 here. You have support for some dynamic shapes. And then you can lower that to Linux if you want. So my own experience with that, and I started out, that was the first importer I used. It's quite stable. It's OK. You have to be a bit careful that the TensorFlow package that you use and the MLIR version that you compiled, that they're in sync, because the dialects change. Now, it probably will get better with the TOSA versioning scheme. The removal of the Python API is a bit annoying and convenient, and I don't think there's a solution to that yet, because now you need to compile TensorFlow from source to use this flow. It's not shipped with the Python packages. Also, the dependency on TensorFlow is even more annoying because you're just using very specific parts of it. Use the deserialization of the flat buffer file and the lowering to TOSA, and the whole ML framework that TensorFlow is, you don't use that. So it's even more annoying. But I think this is the easiest way when you want to try fully integer networks, because also function arguments, function return values are all handled by the TF Lite quantizer. And I think it's easier to export an integer network with that. Let's talk about ONNX, the other file format. So ONNX stands for Open Neural Network Exchange Format. And this time you have a protocol buffer file, which normally ends with an ONNX. This represents static computation graphs. ONNX was built so you can share your model across frameworks, but also you can send it as a file, and makes handling neural networks a lot easier. It's designed for interoperability. If you want to execute that, you probably need to use other projects, such as ONNX Runtime, things like that. And you can also export training graphs with ONNX. So you have to be careful when exporting that you don't have training nodes if you want to do inference. ONNX has two ways of importing to Upstream MLIR. The original one was via ONNX-MLIR. ONNX-MLIR is quite an old MLIR project now. It started at IBM, and it has an LLVM backend to target CPUs, but also a fully code-gen backend for the IBM Telum accelerator. There's a lowering from ONNX to TOSA, but it's incomplete, which is kind of my fault. I did that at my previous day job, but left the company, and since then no one picked it up. There's also a way from ONNX-MLIR to stable HLO to Linux. I've never tried that path, and you also have to have another dependency on stable HLO. But looking through the code, it seems like that one is a bit more complete. To use that, you have to first deserialize the file again, and then convert ONNX to TOSA. And at the bottom, you just have a small snippet of the IR that ONNX-MLIR uses, which is almost a one-to-one mapping to ONNX nodes. And then you have the new way of doing it, via torch.MLIR. This is like the new kid on the block. Two main reasons for that. ONNX and A10, they're quite similar. For example, for convolutions, you have the same data layout. Also, it's very easy normally to map ONNX nodes to A10 nodes, or the other way around, which is actually more common, to export the torch model as ONNX. The second reason was that people didn't want to have three dependencies on big MLIR projects. They had TensorFlow, ONNX-MLIR, and Torch.MLIR. Keeping them all in sync on the same LLVM commit, plus your own downstream stuff, was quite of a hassle. So there's now a deserializer in Torch.MLIR, so you can remove the dependency on ONNX-MLIR. How that works is that you import your ONNX model to an ONNX Torch dialect, which is shown on the bottom. It's modeled with Torch custom ops, so it's not really a dialect, but it's a one-to-one mapping to ONNX nodes. And then you convert that one to the Torch A10 or Torch dialect, and this dialect can be then converted to Linux and TOSA. So you kind of go sideways first and then down. So my own experiences with both of them is that they're both not perfect. So ONNX-MLIR is incomplete, and Torch.MLIR, at least for the models we try, we see failures sometimes. But it gets a lot better. For ONNX-MLIR, try to use the stable HLO path. With the TOSA path is not enough. But the nice thing about using Torch.MLIR is that you get 2 for 1, right? You have ONNX and Torch support just by depending on Torch.MLIR. Also, the ONNX representation is a bit weird in Torch.MLIR with the custom ops. You kinda would expect to have a dialect for that, but I also get why you don't want to do it, because then you would need to auto-generate a table gen file that then is in the build process for the C++ dialect. Maybe IRDL could solve something like that, but it's also not ready yet, so this was the pragmatic choice. Just use ONNX custom ops. Also, the lowering, if you look for it, it's quite interesting because it's just alphabetically ordered. So you have one file going from A to, I don't know, K. Next file goes from K to Q and whatever. And it's just a huge switch statement on the operator string. Let's come to the most complicated one, Torch. So everyone knows Torch, right? It gets, like, our whole LLM world is now powered by Torch. It's a Python-first approach, and there's a lot of hidden C++ code in Torch. You have, over time, you had multiple export formats, Torch script, ONNX, and the FX graph. But the new one introduced after Torch 2.0 is Torch.export. Torch is extremely popular in research and production deployments. But the Torch.export path doesn't have a stable serialization format, so you cannot save your model as a file. This one, it's experimental, it changes very often, so I don't know, maybe if you see that in half a year, it's ready. But right now, it's not. And Torch is even more complicated, because now it's split into 2 parts. You have one part depending on the PyTorch infrastructure, and then you have parts living in Torch.MLIR. So now Torch.export is the default way of exporting a model, and it's a tracing exporting format. So you give your model plus some fake arguments, and you execute that model with fake nodes, and you can track if you have mutable buffers and things like that. You cannot have control flow on tensor elements. This will create what we call a graph break, and the model is not exportable. But this also gives the user a lot of freedom. And then in Torch.MLIR, you have the FX importer, which takes the exported graph and outputs Torch dialect. It also has some hooks for very advanced features like mutable buffers that are not that easy to represent if you're only in upstream dialect tensor world. All of this is non-trivial because you have mutable buffers, dynamic shapes, mixed precision things, and now not the compiler decides that, but the person who wrote the model. So let's see an example. Like I said, you have to have the model somehow in your file or in your Python packages. So this is a very easy, basic NN.module just with one operator. Then the interesting thing is you see batch, channel, and dynamic shapes. So you can now say, hey, batch and channel, they are dynamic, but they're also constrained. So you can say, like, this is a maximum of 10, minimum of 2. And it's actually linear. So you can even say it's a multiple of 16. You give that then to a function that lives on Torch.MLIR called fx export and import. What this does under the hood, it uses Torch.export to export your neural network, and then calls the fx importer to import your model into the dialect. If you look at the lit test on top, you can see that in the IR, we actually have the symbolic shapes that represent that we put constraints on our dynamic dimensions. So if you build a compiler, you actually have 2 choices. You ignore that, or you can use that, for example, to limit allocation sizes. Or if you have multiple of 16, for example, you can even say, hey, I know this will be tileable by 16, even though it's dynamic. So this is very powerful. Then when you have the Torch dialect, which is on top, you can lower that to TOSA or to Linux. Torch.MLIR and the Torch dialect, they have their own type system. which means you also have a type converter, and you also have passes making sure that the function arguments and the return values are in tensor types when you want to go to upstream dialects. So it's not a single pass, it's a pass pipeline, but it's very conveniently wrapped into one command. And it's a torch back into TOSA backend pipeline. And then you have TOSA code at the bottom. Same thing goes for LINAC. It's LINAC on Tensor's backend then. So I spent most of my time actually on this one here. And in my opinion, torch.export is super powerful in what it can capture. The graph breaks are a bit annoying, but this kind of offloads the burden on the model developer. So you cannot fix that, or if you want to fix things in torch.export, you have to contribute to PyTorch. Also, because of all the things I talked about, symbolic shapes, constrained dynamic dimensions, mixed precision, all of that means that a torch frontend by design is more complicated than a TF Lite frontend. I think the fx import is quite nice, and that the hooks can be used like a plugin for your own compiler or for your own implementation are very convenient. I think at the moment, if you use something like mutable buffers, it's not fully supported if you go to LINAC vanilla. Torch to LINAC, in my opinion, has a better coverage than Torch to TOSA. Also comes down to TOSA being tied to a spec and allowing less operations or variants of operations, whereas LINAC, you can do whatever you want. The code quality in some parts is an issue, actually. So when you find a bug, for example, in a convolution lowering to LINAC, super hard to fix, super hard to add new features. Most of the time, this works, though. So we've seen, like, with a few fixes, it's workable. I think large parts of this comes from a large redesign that Torch.MLIR had a few years ago, which pushed it from also having backends to a more pure front-end project. Also keep in mind, if you want to use TOSA, convolutions and pooling operations have different data layouts. So you will see a lot of transposes in your IR, and you need to optimize them away somehow. Let's come to JAX. So with JAX, I have the least experience with. But I tried it out for this talk, and it's actually quite nice. I liked it. It feels like NumPy accelerated by XLA, and it also supports auto-differentiation, so you don't have to implement a backwards version of your operator. It's used in research and large scale-out transformers, but I think mostly by Google to target the TPUs. And it's a very native integration with MLIR. So the code you see here is directly from the website. I just put two code snippets together, and I'm downloading ResNet 18 from Hugging Face, exporting that to stable HLO, and worked out of the box, no issues there. So that was nice, but I also didn't try very advanced features like dynamic shapes or things like that. Then you need to depend on stable HLO. I don't know if stable HLO has a Python library that you can just pip install. I don't think so. So you have to build it from source. And then you can lower from stable HLO to TOSA or to LINAC. And the LINAC one is quite complete. Like I said, I don't have too much experience with it, but it looked good so far. Don't have problems with it. So in summary, if you want to import a model, you have to choose the correct importing project for it. If you have LiteRT, use TensorFlow, unfortunately. And ONNX, you can choose Torch.MLIR, ONNX-MLIR, Torch, of course, Torch.MLIR, and JAX would be stable HLO. The easy cases most often work for all of those four. But the devil is in the detail, especially with Torch, when you give the ML developer so much power. You can very often choose between TOSA or LINAC. And what I saw across the projects is that normally the LINAC coverage is a bit better. However, TOSA also has the use cases because it's a very reduced operator set. Also, it's a bit annoying that you need to build so many projects on top of MLIR from source just to import your model. I don't think it's very beginner-friendly. Torch.MLIR at least has a pip package that you can install, but with TensorFlow and the removal of the Python API, that was a bit annoying. Yeah, so if you have any questions, happy to connect, and thanks for listening.
Maximilian. Questions, please. Hi, nice talk. I was wondering what happens in the torch flow if you have just-in-time components like torch compile or Triton JIT. Does the exporter support those and the importer as well?
So torch compile uses a lot of the same infrastructure under the hood, but it also handles graph breaks. So what torch compile does, it then stitches together two graphs and executes the Python line that was not traceable. So in a sense, torch compile has a bigger coverage, but it also has performance hits. And as far as I know, Triton has its own flow, but I'm not super sure. I'm not a Triton expert.
Okay, I was just wondering if they create some kind of custom operator thing in the graph, like a node, in any way.
No, unfortunately not. If you see graph breaks, there's something like a dictionary of what you can do to fix that from Torch. But I mean, what we did, we went to transformers and fixed a few models in transformers and things like that.
Okay, thanks.
How do the different importers compare when it comes to weights? Are they exposed as constants that you can, for example, optimize the transpose at compile time, or are they just exposed as parameters to the function?
In the ONNX-MLIR and LiteRT importer, they're in DIR as constant ops. And torch.MLIR, you can offload them to the resource part of the IR, or you can even save them in a different file. So you can compile your model without the weights, but they're not arguments to the function. It's more like you have operations like a global load thing that retrieves the constant.
Okay, thanks.
Yeah, I guess I just want to comment that for the Triton one, it'll kind of export it as a custom higher order op, and you're responsible for building a custom torch extension that interfaces with that. So it's a little hacky as far as you gotta plug it in, but yeah, that's what it does. But I was gonna ask, so I had this problem where for torch export, it always unrolls every single NN module, and it looks like by design it can't just give you a for loop to loop over NN modules, and if you have instruction kind of in general, unrolling models can get very large as far as IR goes, and so is there kind of an effort to allow for it to just be nested for loops for just at each NN module? Because such a large binary could be a little performance inefficient.
I'm not completely sure. So I know that you can tell torch.export which decompositions to use, and the normal set is quite broad. So it might be that your for loops are just decomposed and you just have to remove that decomposition. But it could also be a more systematic issue in Torch. They're working really hard on it. Execute Torch also depends on Torch export, so they try to fix that.
Okay, thank you.
Let's thank Maximilian for a good talk.